We're considering 4 particles that can be distributed between 2 boxes. The result is 16 different microstates that we see here, and they are separated into 5 distributions. We can label the distributions 4, 0, 3, 1, 2, 2, 1, 3, and 0, 4 according to the number of particles in each respective box. We can calculate the number of microstates by raising n to the n power. Here, lowercase n is the number of possible boxes, here 2, and n uppercase corresponds to the number of particles, 4. So this corresponds to 16 possible microstates. Boltzmann argued that entropy can be given by K times ln of W, where W is the number of microstates. So the distribution that has the greatest entropy will be the one that has the greatest number of microstates. In this case, the distribution with the greatest entropy is an even distribution because it contains 6 out of the 16 microstates, or a 3/8 probability. Here we see the same microstates, and we're going to calculate some numerical values for the change in entropy. The Boltzmann equation is that the entropy is equal to K times the natural log of the number of microstates. And keep in mind that K is the Boltzmann constant. Now we can note that delta S ought to be a positive value because we're going to a system where there's more possible microstates, a higher probability system. Delta S as a state function is going to be the final state minus the initial state. In the final state we have 6 possible microstates, and initially we only have the 1. We can substitute in the relevant values, take advantage of the property of logs, and calculate out our final value. As we see, delta S is a positive value as we expected. In this next problem, we're asked to calculate the entropy associated with the change, where all the particles are initially evenly distributed and all end up in a single box, which is going to be on the right-hand side. So this is essentially the reverse of this process. So we would arrive at an answer opposite but equal in magnitude to the prior situation. Finally, we want to consider the change where the system is converted from B to D. As we see, situation B is a 3-1, and it's essentially equivalent to a 1-3 situation. Each of these have 4 associated microstates. And here we see we have no change in entropy. We have the same number of microstates in the final situation as the initial situation. The natural log of 4 over 4 is going to go to 0, so delta S is 0 as expected. Let's go back to considering probabilities. The total number of microstates can be given by n raised to the n power. N here is 2. There's 2 boxes, and if we consider only 4 particles, the result is going to be 2 raised to the 4th power, which is our 16 possible microstates. Of these 16 possible microstates, there are 2, A and E, that have all 4 particles in one of the 2 boxes. So the total probability of having all particles in one of the boxes is 1/8. Let's go on and consider 6 particles. The difference being that there will be a greater number of possible microstates. So there's 64 possible microstates. Only 2 correspond to having all particles in one box. So we have a 1 over 64 plus a 1 over 64 to correspond to a 1/32nd probability of all of the particles being in one box. So we see we've gone to a much lower probability of all particles being in one box by only adding 6 additional particles. Let's look at 30 particles. Let's assume we have 30 particles that are initially evenly distributed between two sides. We can call these two boxes. What's the likelihood that they will all spontaneously be found in only one of the two boxes? And here the number of possible microstates corresponds to 1 billion different microstates, only 2 of which correspond to all the particles in one side. So the related probability is only a 2 in 1 billion chance that all the particles will spontaneously be on one side of the box, and that is vanishingly small. Okay, we'll call that negligible. Okay, and this corresponds to still a relatively small number of particles. So if we expand this to a real-life situation, the probability of this event happening is vanishingly small.